Like other infiltration models, Kostiakov'S works on reconfiguring the model into the best fit line format. What are the significant changes in the procedure? Find them out here in hydrology. Given the time since the start of storm in hours and the cumulative depth in millimeters, we are to look for the function using Kostiakov'S equation. What we have are time, which is the independent variable, and the accumulated infiltration depth as the dependent variable. However, we cannot readily use these inputs in taking the best fit line, as we are to configure the function based on Kostiakov'S equation, which is f sub p as equated to a times t raised to b. So the first thing to do is to jive the two equations and make them similar. We are to transform Kostiakov'S equation into the slope-intercept form of y is equal to mx plus b, and that is by taking the logarithm of the equation, making ln of f sub p as equal to the ln of a times t raised to b. The logarithm of a product can then be expanded into ln of the first term a plus ln of the second term t raised to b. Then, with the power rule, we can rewrite the second term, making ln of f sub p as equal to ln of a plus b multiplied by ln of t. Now we have two terms combined by a plus, similar with the line formula. So we can then take y as ln of f sub p and x as ln of t. These are the two parameters we need in curve fitting. So let's create the x and y parameters, starting with y, which is equal to ln of f sub p. What we are provided is the table for cumulative time and cumulative depth. From this, we look for ln of f sub p, but the infiltration capacity, small f sub p, is the ratio of the incremental depth and the incremental time. This means that from the provided values, we convert cumulative time into incremental time, where the first is 1 minus 0, giving 1. The next is 2 minus 1, which is 1. And since the cumulative time is placed in chronological order, with regular interval, we can write the incremental time as 1 from the start until the end. This then completes the denominator for f sub p. Now for the numerator, incremental depth. The table we have is cumulative depth, which means we are to have another column for incremental depth, and the procedure is similar with what we did with time earlier. So take the initial depth as 12, then take the difference of the two consecutive inputs, such as 19.5 minus 12, which is 7.5, then 24.6 less 19.5, which is 5.1. Next is 32.8 less 24.6, giving 8.2. Then 41.5 minus 32.8 as 8.7. Followed by 49.8 less 41.5, giving 8.3. Then 58.7 minus 49.8 as 8.9. There is also 67.5 minus 58.7, which is 8.8. Then 75.4 less 67.5, and that is 7.9. And lastly, 80.6 minus 75.4 is 5.2. Having completed both incremental depth and time, we can then compute for the infiltration capacity f sub p by taking the ratio of the two quantities. That starts with 12 upon 1 as 12. Then 7.5 divided by 1 is 7.5. Next is 5.1 divided by 1 as 5.1. 8.2 over 1 as 8.2. 8.7 upon 1 as 8.7. Then 8.3 divided by 1 as 8.3. Then there are also 8.9 divided by 1 as 8.9. 8.8 over 1 as 8.8. 7.9 upon 1 as 7.9. Then lastly, 5.2 divided by 1 as 5.2. This is infiltration capacity, but notated as small f sub p, as they are the incremental infiltration capacity. What we are required is the cumulative infiltration capacity, noted as capital F sub p. So we then convert incremental infiltration capacity into accumulated infiltration capacity, which is notated as capital F sub p. When we say cumulative, we only need to add consecutive inputs, where we start with the initial capacity of 12. Then 12 plus 7.5 is 19.5. Then add 5.1 to the total to get 24.6. And again, add 8.2 to get 32.8. And also place 8.7 next to get 41.5. The next to add is 8.3, which is 49.8. And place 8.9, giving 58.7. Then add 8.8 to have 67.5 plus 7.9 to get 75.4. Then lastly, add 5.2 to get 80.6. This is the completed cumulative infiltration capacity. But from the reconfiguration of Kostiakov'S model, what we needed is ln of f sub p. So place another column and take ln of 12, which is 2.4849. The ln of 19.5 is 2.9704. Ln of 24.6 is 3.2027. The ln of 32.8 is 3.4904. Ln of 41.5 is 3.7257. The ln of 49.8 is 3.9080. The ln of 58.7 is 4.0724. Ln of 67.5 is 4.2121. The ln of 75.4 is 4.3228. Then ln of 80.6 is 4.3895. This column is the dependent variable y in the analysis of the best fit line. Next, we move on to the determination of the x variable, which we found to be ln of t. From the existing table we have created, there are two columns for time. One is the cumulative time, and the other is the incremental time. Which of these columns are we to take logarithms of? Note that the x-axis in the graph should be increasing, regardless of the values from the ordinate. So what we should place is the logarithm of the accumulated time. So ln of 1 is 0. Ln of 2 is 0.6931. Ln of 3 is 1.0986. The ln of 4 is 1.3863. Ln of 5 is 1.6094. The ln of 6 is 1.7918. Ln of 7 is 1.9459. The ln of 8 is 2.0794. Ln of 9 is 2.1972. Ln of 10 is 2.3026. We have then completed the two variables for curve fitting. For discussion, we plot the points in the graph, where the x-axis is ln of time, and the y-axis is the logarithm of the accumulated infiltration capacity. The first point is located at 0 and 12, then 0.6931 and 19.5, followed by the third point at 1.0986 and 24.6, then 1.3863 with 32.8. Next is at 1.6094 and 41.5 with 1.17918 and 49.8. There is also a point at 1.9459 and 58.7 and 2.0794 and 67.5. Then also 2.1972 and 75.4. And the last is at 2.3026 and 80.6. Note that the points are somehow scattered, but in order to have a function for this plot, we take the best fit line, where the format for the function is y is equal to mx plus b. Given the values for ln of t as x and ln of f of p as y, solve for the function of the dataset, where we use the principle of least squares. This is the simplest method, as there is a readily available equation for slope, which is n times the summation of xy less the product of the summations of x and y, all upon the number of entries n, times the summation of the square of x minus the square of the summation of x. From this equation, there is summation of xy, which means we can place another column to solve for xy, and eventually take their summation later. For this example, xy starts with 0 times 12, which is 0, all the way to the bottom with 2.3026 times 80.6, which is 185.5896. There is another entity of x squared, which requires another column, starting with the square of 0, which is 0, followed by the others until the square of 2.3026, which is 5.3020. Now take the summation of each column, providing 15.1043 for x, 462.4 for y, then 847.8757 for xy, and 27.6499 for x squared. The slope m is then solved as 10 times 847.8757 less the product of 15.1043 and 462.4, all upon 10 times 27.6499 less the square of 15.1043, which results to 30.90453869, taken wholly, as these values again used to look for b later. The y-intercept b is solved as the summation of y minus the slope times the summation of x all over the number of entries. Plugging the values, b is solved as 462.4 minus 30.90453869 times 15.1043 all over 10, giving negative 0.4391. So the best fit curve is y is equal to 30.9045x minus 0.4391. So from the best fit line of y is equal to 30.9045x minus 0.4391, we then convert this back to Kostiakov'S configuration, where we start with ln of fp is equal to ln of a plus b times ln of t. By analogy, we can take ln of a as negative 0.4391, where we take the value of a by plugging in Euler's number e. A is then e raised to negative 0.4391, which is simplified as 0.6446. From the equations, b is also equal to 30.9045, where we take this as it is. With a and b already figured out, we plug them in Kostiakov'S model of f of p as equal to a times t raised to b, making it f of p as 0.6446t raised to 30.9045.